This is an LED. LEDs are one of my favourite electronic components, and in fact I'd go as far as to say that I really do love LEDs. This particular LED that we see in front of us is a slow colour changing LED, and I'll talk about these a little more later. This LED fades through a variety of different colours, and the camera really isn't doing justice to the beautiful colours that this LED emits. Of course, LEDs had a much more humble start. While electroluminescence had been known about since the early 1900s, it wasn't until the 1960s that a practical LED was produced, and it wasn't until the 1970s when commercially available LEDs really took off. I don't have any LEDs from the 1960s, but I do have some from the 1970s and 80s, so let's take a look at some examples now. This one here is a fairly early LED, and if I show it to the camera, you can see this LED is very dim. If we take a look at a slightly newer LED, we can see this one here from the 1980s does produce a lot more light from the same coin cell battery. Of course, modern LEDs can produce a lot more light for the same power input. This is an example of a high brightness LED. Back in the 1970s, LEDs were still quite expensive. In 1975, an individual LED might set you back as much as £1, and accounting for inflation, that's the equivalent of around £8 per LED today. By 1983, if you weren't picky about the form factor, you could pick up 4 LEDs for as little as 69 pence. Again, that's around £2.40 in today's money, or 60p per LED. Of course, modern LEDs are far, far cheaper. I picked up 100 of these high brightness red LEDs for just 90 pence. That's less than 1p per LED. Modern LEDs are available in a variety of colours, and we can see a few examples here on the table in front of me. Even back in the 1970s, green LEDs were commonly available, and here is a modern example. We also have yellow LEDs, orange or amber LEDs, and even blue LEDs, which were only invented in the 1990s. LEDs are extensively used as indicators, but there is one potential problem with that. LEDs only work one way round. In the correct orientation, they light as expected, but if I turn the LED round, you'll see I get no illumination. However, some LEDs do actually work in both directions. This one here is actually an example of a bi-directional LED. As you can see, it illuminates this way round, and if I flip it, it illuminates in this direction as well. So how does this work? Well, this LED actually has 2 LEDs in reverse parallel. That means that in one direction, one of the LEDs lights, and in the reverse direction, the other LED illuminates. Of course, if we're putting 2 LEDs in the same package, there's no reason they have to be the same colour. This LED combines 2 different coloured chips. In the normal direction, it illuminates red, but if I turn the LED round, it illuminates green. If we want more control over the individual LEDs, we can simply add more leads to the package. This LED here actually combines 2 LEDs as well. On one side we have the green LED, and on the other side here we have the red LED. This means that if we combine them, we can actually blend the colours that they produce. Here we're getting a kind of yellowy colour. These bicolour or tricolour LEDs were mentioned back in the 1983 catalogue I just showed you. In 1983, these would set you back around £1.20, which is the equivalent of around £4 today. However, just last year I picked up 200 of these bicolour LEDs for just £5.35, and that works out at less than 3 pence per LED. With the advent of blue LEDs, we now combine red, green and blue LEDs into a single package, and this allows us to merge these colours in different ratios to produce any colour we would like. Here is an RGB LED. Here we have green, and blue, and red. Today it's extremely common to use LEDs for general purpose illumination. In that application, we tend to use ultraviolet LEDs and coat them with a special phosphor. This allows us to produce rich, warm white light that we used to produce using incandescent filaments. I have a few LED filament bars on the table just here. Using my multimeter set to diode test mode, I can go ahead and test that LED. Here you can see this LED is gently illuminating. In my videos, I often test LEDs by placing them directly across a CR2032 coin cell battery, like so. As you can see, this allows me to test the LED. However, I regularly get comments advising me that placing an LED directly across a battery is inadvisable, and those comments are absolutely correct. However, coin cell batteries such as these have high enough internal resistance that they are unable to provide sufficient current to damage most LEDs, and as such, it's perfectly safe, generally, to place an LED across the CR2032 coin cell. However, not all batteries are created equally. Here I have two examples of the common 9V PP3 battery. In my left hand I have one by Panasonic, and in my right hand one by Duracell. However, it's not the brands here that are important, but rather the battery chemistry. If we look closely at the Panasonic, we can see this is a zinc-carbon battery. And if we look more closely at the Duracell here, we can see the chemistry of this one is alkaline. Here I have the same high brightness red LED that I was just testing with the CR2032 coin cell battery. But this time I'm going to put it directly across the terminals of this 9V battery. Generally this would be a very bad idea, but let's give it a go anyway. As you can see, the LED lights just fine. While this would normally be problematic, because this battery is zinc carbon, it doesn't actually produce enough current to damage this particular LED. Now let's try the same experiment with the alkaline battery. You may have seen a very brief pulse of light, and that's because this LED has now been damaged and will no longer work. The alkaline battery provides so much current that it causes the LED element inside to overheat and burn out. If we try and test it now with a regular CR2032 battery, we'll see that it no longer works at all. While on this occasion the failure mode was rather unexciting, it is possible that an LED may actually explode when provided with too much current. For this reason, you should always use a current-limiting resistor with an LED. I'll provide a link to a website that can help you calculate the required resistor value in the video description. However, every rule has an exception, and it turns out that some LEDs can be safely placed across high current, high voltage sources. This green LED here is one such example. Taking our alkaline battery, here I can connect this directly across the terminals. As you can see, the LED lights just fine, and I could leave it connected here as long as I like. That's because this LED actually has a built-in resistor. With modern electronics, it's possible to embed tiny little components next to the LED chip directly in the head of the LED. One of the most common uses for LEDs is as indicators. Many devices and products contain numerous LEDs that might light up in different quantities or in different colours to indicate different states. One popular way of controlling that is by using a microcontroller, and for development purposes you might choose to use something like this Arduino Uno. Earlier we talked about bicolour LEDs, and this is an example that contains two LEDs in a single package. We might want red to say indicate that something requires charging, and green to say it's finished charging. So let's pop it in the Arduino with some code running to see what happens. Here we can light up the LED in one of two states. Of course, we can do the same trick with the bicolour LED with only two legs. Let's pop it in this part of the board here. Here we see each LED illuminating in opposite colours. However, that is just an artifact of the orientation of the LED. If I turn this round, both LEDs will illuminate the same colour. By carefully fading between two different colour states, we can actually produce the intermediate colours. Here we can see this happening with the 3-leg LED, and it's also possible with the 2-leg version as well. Of course, with modern RGB LEDs, we might want to control a whole host of different colours. Now this allows us to pick any colour we'd like at all from the rainbow. Now this works reasonably well, but what if we wanted to control lots of LEDs at once? Well, if all the LEDs were going to be the same colour, maybe that won't be a problem. But what if we wanted different colours for each LEDs? Fortunately, there is a solution. Here I have a modern LED stick. This is using the W2812B RGB LED. These are sometimes known by the brand name NeoPixels. As you can see, there are only 3 connectors on this LED bar, and there are actually 10 LEDs on this strip. 2 of those connectors are for power and ground, and the third provides data. If I plug it into the microcontroller here, we can control every single one of those LEDs individually. Here we can see a really attractive rainbow LED effect, where each LED on the bar is a different colour, and the camera really isn't doing this justice. Each of the LEDs is getting an individual colour command over that single data wire. This works because each LED actually has a tiny microcontroller of its own embedded in the chip. The way this works is that each LED strips off the first chunk of colour information before passing the rest of the data to the next LED in the chain. If you provide 10 chunks of colour information, that means you can control the colour of 10 independent LEDs, simply by passing the data from one LED to the next. But if each LED contains its own microcontroller, surely having this whole microcontroller here to control the LEDs is a little bit overspecified. It turns out that a few of the LEDs on the table in front of me actually contain their own microcontrollers. So let's take a quick look. This tiny clear LED here is actually a multicoloured LED. And as you can see, it flashes through a wide variety of bright coloured patterns. I also have this LED that fades through the colours much more slowly. And you can get examples like this one that use a cloudy or translucent package, and this enhances the effect of blending the different colours. I think one of the most exciting things you can do with an LED is to flash it on and off. Here is a very simple flashing LED circuit. This is based on what's called a relaxation oscillator, and it very cleverly uses the transistor here in the reverse orientation and doesn't connect the base. I first heard about this circuit around 10 years ago, right here on YouTube, and I'll provide a link to that video if you'd like to learn more about the circuit in the same way that I did. But for now, let's take a look at it in operation. Here we can see the LED slowly flashing. But let's take a closer look at the operation of this circuit. As you can see, for this circuit to operate, I have to run it at 13.5 volts. The circuit is very sensitive to the component values and the input voltage. Let's take a closer look with an oscilloscope. The way the circuit works is that the capacitor charges up through the 1K resistor. Once this level exceeds the reverse breakdown voltage of the base emitter junction, the transistor begins conducting in the reverse direction. Due to the negative resistance property of this small region of the transistor, the capacitor quickly discharges through the LED and through the 220 ohm current limiting resistor. At this point, the transistor then stops conducting, this turns off the LED and allows the capacitor to recharge. Because of the very narrow region in which the transistor exhibits this negative resistance property, the LED itself is a crucial component in the configuration of this circuit. So let's see what happens when we substitute the LED. Here I have our bicolour LED. Let's try this one in the circuit. As you can see in the green orientation, it works as expected. But in the red orientation, the pulses are much more erratic. One of my favourite types of LED are these slowly fading colour changing ones. Unfortunately, whenever you turn these on and off, they reset back to their default colour. That means that if we turn this on and off rapidly, we just end up with a flashing red LED, and that's really selling this kind of LED short. However, let's see what happens when we place it in the flashing circuit. As you can see, just like with our bicolour LED, we end up with a much more erratic pulse duration. However, interestingly, the LED doesn't always reset to red. Instead, we see it flash on and off with different colours. So let's take a closer look with the oscilloscope and see if we can work out why. As we can see on the display, we end up with highly variable LED pulse width duration. And that's because each LED coloured element inside the LED body actually affects the circuit differently. Certain colours, such as blue or white when we're trying to illuminate all three of the LED chips simultaneously, draw much more power, and this means that the pulse width duration is much shorter. However, the green element, and the red element in particular, can operate from much lower power levels, and that means that when we have green or red, the pulse is much longer in duration. But why doesn't the LED just flash red, as we saw when we connected it directly across the battery? Well, if you look closely at the oscilloscope, we can see the voltage level actually doesn't dip down to zero. Once the tiny microcontroller embedded in the device is no longer able to drive the LED elements, this becomes an extremely low current path. By carefully choosing the value of the discharge resistor, we've created a voltage divider. In this circuit, that means there's sufficient voltage across the LED device to maintain the state in the microcontroller. However, this value is outside of the negative resistance region of the transistor, and that means the oscillator can reset. Fortunately, the microcontroller inside the LED is able to maintain its state with just that residual voltage level and any leakage current that happens to be flowing through the transistor. While this circuit does actually work, everything about this circuit is the misuse or even abuse of these components. Nonetheless, I hope you found this exploration of LEDs and this really unusual oscillator circuit interesting, and I hope to speak to you again soon in the next video.